Welcome to this tutorial on Java variables and data types. Understanding how variables work and the different data types available in Java is fundamental to writing effective programs. Let's dive into the core concepts that every Java programmer needs to know. Java offers 8 primitive data types that are used for storing simple values. Let's look at each one in detail. The byte data type uses 8 bits of memory and can store whole numbers from -128 to 127. It's perfect for saving memory when you know a number will be within this small range, like counters in small loops. The short data type uses 16 bits and can hold values from -32,768 to 32,767. It's useful when byte is too small, but int would be overkill, such as storing age or year values. The int data type is the most commonly used integer type with 32 bits, handling numbers from negative to positive 2 billion. This is your go-to choice for most whole numbers like quantities, counts, or indices. The long data type provides 64 bits for storing integers from -9 quintillion to +9 quintillion. It's essential when working with very large numbers, like population counts or astronomical distances. For decimal numbers, the float data type uses 32 bits, providing about 7 digits of precision. You'll notice that float literals end with f, like 3.14f. It's useful for scientific calculations where memory efficiency matters more than precision. The double data type offers more precision with 64 bits, giving about 15 digits of decimal precision. It's the default choice for decimal values in Java and ideal for financial calculations or any situation requiring high precision. The char data type uses 16 bits to store a single Unicode character, enclosed in single quotes like a. This allows Java to support characters from almost all written languages worldwide. Finally, the Boolean data type is the simplest, requiring just 1 bit conceptually to store either true or false. It's essential for conditional logic, flags, and control flow. Each primitive type has a specific size in memory, making them efficient and fast. Looking at some practical examples, we can declare variables of different primitive types. Here we have an int for storing age, a double for salary with decimal precision, a char for a single character like a grade, and a Boolean that simply holds true or false. When a primitive variable is created, Java allocates memory based on the data type. For instance, an integer like age with the value 25 takes up 4 bytes of memory. This memory block stores the variable name, its type, value, and size information directly in memory, making primitive types very efficient for basic data storage and manipulation. In Java, working with variables involves 2 key steps: declaration and initialization. Let's explore these concepts in more detail. When you declare a variable, you're telling Java to reserve memory for a value of a specific type. For example, with int score, Java sets aside space for an integer called score, but no value is assigned yet. At this stage, the variable exists but contains a default value, 0 for numeric types, or is considered uninitialized in local scopes, meaning you can't use it until you give it a proper value. Initialization is the process of giving a variable its first value. After declaring score, we can initialize it with score equals 100. Now the memory space contains the actual value 100, and the variable is ready to be used in calculations, comparisons, or any other operations. Java also allows you to perform both steps at once with a combined declaration and initialization. As you can see in int highscore equals 500, we're both reserving memory and assigning a value in a single statement. This is not just more concise, but also more efficient since Java can optimize the memory allocation, knowing the initial value up front. This approach streamlines your code and ensures variables have valid values from the start. It's often preferred in Java programming to declare and initialize variables in one step when possible, especially when the initial value is known at the time of declaration. This practice helps prevent bugs related to uninitialized variables and makes code more readable by clearly showing the intended starting value. Typecasting in Java allows you to convert a value from one data type to another. There are 2 types of casting, implicit and explicit. Implicit casting, also known as widening conversion, happens automatically when you convert from a smaller data type to a larger one. For example, when you assign a byte to an int, Java automatically converts it since an int can easily hold any byte value. There's plenty of room in the larger container. The same applies as we progress from int to long, long to float, and float to double. The important thing to note is that no data is lost during implicit casting because we're moving to a larger container. Java handles this conversion seamlessly without requiring any special syntax. Explicit casting, or narrowing conversion, is required when you convert from a larger data type to a smaller one. For instance, to convert a double to a float, you must use explicit syntax like float d. This tells Java that you're aware data might be lost, but you want to proceed anyway. The cast operator in parentheses effectively says, I know what I'm doing here. As we convert from double to float, float to long, long to int, and finally int to byte, we risk losing precision or changing the value entirely. In our example, the double value 100.99 becomes just 100 when cast to an int because the decimal portion is truncated. It's crucial to be cautious with explicit casting. Always consider whether the target type can properly represent the original value to avoid unexpected results in your programs. For instance, casting a large integer to a byte could result in a completely different value due to overflow. This is why Java requires you to be explicit. It's a way of confirming that you understand and accept the potential consequences of the conversion. Unlike primitive types, reference types in Java don't store their values directly in the variable. Instead, they store references, or addresses, to objects in memory. The main reference types in Java include string, arrays, classes, and interfaces. Let's start with string, which is one of the most commonly used reference types. When you create a string with string name equals Java, Java allocates memory in two locations. In the stack memory, a variable named name is created, but it doesn't contain the actual text. Instead, it stores a reference to the heap memory where the string Java is actually stored. This reference works like an address, pointing to where the real data lives. Strings are used to store text of any length, from single words to entire paragraphs. We'll explore strings in much more depth in a future video, including methods for manipulation, comparison, and the special immutable nature of Java strings. Arrays work similarly. With int, scores equals 85, 90, 78, 92. The variable scores in the stack only contains a reference to the array elements stored in the heap. Each element can be accessed using its index, starting from 0. Arrays are perfect for storing collections of values of the same type, whether primitive or reference types. In an upcoming video, we'll cover arrays extensively, including multidimensional arrays, array manipulation, and common algorithms for searching and sorting. When working with custom classes like person, the same pattern applies. Here, person student equals new person, John 20, creates a student variable in the stack that references a person object in the heap. This object contains multiple properties, such as name and age, all accessible through the reference. Classes are the foundation of object-oriented programming in Java, allowing you to create custom data types with both attributes and behaviors. We'll have a dedicated video series on classes, covering everything from basic class structure to inheritance, encapsulation, and polymorphism. Interfaces demonstrate polymorphism in Java. With runnable task equals new myTask, the task variable references an object that implements the runnable interface. Interfaces define a contract that implementing classes must fulfill, enabling different objects to be used interchangeably. This is a powerful concept that promotes flexible, modular code design. Our future video on interfaces will explore how they enable loose coupling between components and support advanced patterns like dependency injection. This reference-based system is powerful because it enables complex data structures and object-oriented programming while efficiently managing memory. It allows multiple variables to reference the same object, creating more flexible and memory-efficient programs. Understanding the distinction between primitive and reference types is crucial for effective Java programming, especially when dealing with method parameters, equality comparisons, and garbage collection. In summary, Java offers both primitive and reference data types, each serving specific purposes in your programs. Primitive types store actual values directly, and are efficient for simple data. Reference types store memory addresses pointing to objects and enable complex structures. Remember that variables must always be declared before use. Explicit casting is required when converting larger types to smaller ones, and memory management differs significantly between primitive and reference types. As you build more complex applications, your understanding of these fundamental concepts will help you write more efficient and error-free code. The key to mastering Java is practice, so experiment with different data types and observe how they behave in various situations. In our upcoming tutorials, we'll explore each reference type in greater detail, diving into the power of string manipulation, efficient array operations, designing effective classes, and leveraging interfaces for flexible code architecture. Each of these topics builds upon the foundation we've established today. Thank you for watching this tutorial on Java variables and data types. Happy coding!